Hello everyone, I'm recording this extra video to show you two more examples about the questions you may see on the midterm. And I have received this kind of request from at least one student, and I understand this is the first exam, and this could be stressful to you guys. I definitely want to give you more ideas about the coming midterm. As I said before, I don't want to surprise my students. Okay, so let's see the first one. So for the first question, given a list of integers as a and the algorithm below sums all the odd values. Okay, so we have a function and it is sum odd values, and we take a parameter as a and we create a sum as 0 and we visit all the values from 1 to n. So we are using the value I as the index, and for each AI we test whether this AI is odd or not. If it is odd, and then we want to add this value to sum, and eventually we return the sum. Okay, really straightforward. This is a CS1 coding, and the question we want to ask is, what is the Tn for this algorithm, and analyze the asymptotic performance of this algorithm. Okay, so let's take a look on my drawing board. And well, I think the first question is, do you want to really count this one, the very first line, as a primitive step? And for my perspective, I wouldn't do so. But if you count this as one, that's also okay. But I'm gonna put a question mark. It depends on you whether you want to count it or not. And for the next line, sum equals 0, that's definitely one primitive step. And how about the next? This is for I from 1 to n. So how many times we are going to execute this line of code? And n times, right? If n is the length of the list A. And then if AI is odd, so we have to grab the value using I as index, and we want to test whether it's an odd value. So for this line, it definitely runs for n times. For every value, we have to test whether AI is an odd value or not. And how about the next line? Well, if AI is indeed an odd value, and then we will go down into this line of code. And my question is, should we count this as n? Question mark. So what's your idea? The answer is yes, we do want to count this as n because we are analyzing the worst case. And then what's the worst case? The worst case is for each value we are visiting, this line will give us a true, so we go down here. So for the worst case, will be a list like this. So for all the values, they are odd, so we have to constantly go to this line of the code. Okay, and then for the return, I will say this is a primitive step. So for the Tn, if we want to add everything together here, I'm gonna skip this one, so I'm gonna get a 3n plus a 2. Is that correct? Okay, so after we have the Tn, and then you have to move on and do the big O. And then how do you do the big O? So for the big O, we are trying to have another well, we can see this is a linear, so it is a ON. So well, we just grab the highest degree of polynomial, and we know that. But how do we prove that? So how about we say we have Fn as n, and then we have a constant C as 10. Okay, so Tn, which is 3n plus 2, is smaller or equal to C multiplied by excuse me, C multiplied by Fn for n greater than n0. And then what should be the n0? And say if we want to n0 to be 1, And in this case, 3n plus a 2 will give us a 5. And then n multiplied by 10 will give us 10. So that is okay. So we can say n0 is 1. Okay, so let me repeat that. We have the Tn, and then we want to find a C value, a Fn, and then n0. So just now we observe that it is linear, so this Fn has to be n. And after that, we do want to have a C which is higher than 3. You can pick 5 or 4 or 7, that's okay. I just want to pick a higher number, so I decide to pick 10. And after that, you have to find an n0 value, so that for all the n value greater than n0, C multiplied by Fn is greater than Tn. So I did some math, and then I find that after n0, after 1 or higher than 1, and then we will always have 10n is greater or equal to 3n plus a 2. So we say O n is for Tn is On. Okay, and then after that, you also want to prove that it is omega n, and then by putting those two information together, we can say this is theta n. Okay, so this is my analysis of this algorithm, and I can prove that this is a linear algorithm. Okay, so this is the first additional question I have prepared, and let me clear everything, and let's move on to the next one. So for the next one, this is a recursive algorithm. This algorithm takes an array A, and then it specifies I and J, saying where to begin, where to end, and it will, as long as I is still smaller than J, and then it wants to swap the value on index I and the value on index J. So we want to do a swap, and after that we want to continue this reverse by doing a recursion. So we are still doing the reverse array, but now I want to move the I cursor up by 1 and the J cursor down by 1. Okay, and then again the requirement is what's the Tn, and then analyze the asymptotic performance of this algorithm. Okay, I didn't specify use the substitution or iteration or the master theorem, so you can decide whichever you want to use. Okay, so let me grab this code. Come on. And okay, just 4 lines of code, right? Okay, and then for the first line, this is the definition of the function, and I wouldn't really count this as a one primitive step. And for this one, okay, this is 1 for sure, because this is a primitive step, and for this swap, it's a primitive step, and then for this and then this is the recursive call. Okay, so before I move on and talk more about how to analyze the Tn, how about I give you an example? Say A equals 1, 3, 7, 11, and 15. And then how do we count this? And let's say we are using the one-based indexing as we used in our textbook. So we want to do a reverse array. And then the first parameter is going to be A. And then from 1 to 5. Are you okay with that? Okay, so this index 1, 2, 3, 4, 5. So the lowest index is 1, and the highest index is 5. And then I want to reverse the A starting from the very beginning at the very end. And then the first step, let me put 1, 3, 7, 11, and 15. Okay, at the very beginning, I is here and J is here. So we want to swap the index, the value on index I and index J. So I'm gonna delete this 5, and then I'm gonna put it here. Okay, I'm being lazy. So we have swapped the very beginning at the very last, and after that, oops, come on. And after that, when we want to do the recursive call, I want to move the I up by 1, and then j down by 1. Okay, so this will be the first recursive call. We are moving the I and j both toward the middle, and then we want to check this condition again, I smaller than j. So yes, so we want to swap the 3 and 11 again. So let me swap the 11 and 3. And after that, we want to do I up by 1 and j down by 1. So eventually you will have I here and j here again. Okay, so let me erase those two I and j. And now we want to go to the next recursive call, and we want to check this line of code. If I is smaller than j, and in this case I equals j, so we are at the base case. So I would call this is a hidden base case because it's not defined explicitly, and for the base case we have nothing to do since I and j they have already met, and we are pointing on the middle value 7. We don't have to do anything, and then that's the end of this recursive algorithm. Okay, so as you can see, we have got all those values reversed. Okay, so let's answer this question. What's the cost of this recursive call? Okay, and originally we want to swap all the 5 values. And after we have done one recursion, what is the problem size? The problem size has reduced from 5 to what? To 3, right? Well, every time when we do a swap, we swap the 2 values and then we go inside, and then the problem size will be reduced by 2. Okay, so if the whole cost of this algorithm is Tn for the total cost of this algorithm, and then for this line of the code, the cost of this recursion will be Tn minus 2. Okay, well, this is a funny Tn because this Tn equals Tn divided by 2 and then plus 2 outside. This means, well, we are still using the getting one step closer mindset of doing the recursion, but not getting one step closer, we are getting 2 steps closer to our goal. Okay, so this is the Tn. And my question is, how do you want to solve this recursion? So master theorem. My first question is, can you use the master theorem? Okay, for the master theorem, we are seeing the Tn like this. So for the Tn, it should be a constant for n equals 1. And then we have the a, t, n divided by b, and plus a fn. Okay, so we have to have this type of the Tn to use the master theorem. But for this Tn we currently have, it's not really on this shape. There is no b value here. That's the painful part. So my answer is, for the master theorem, that's not the way to go. So you have to decide if you want to use the substitution or the recursion. And I would say using substitution is kind of a overkill. We can do the iteration. So say t and divide by 4 and then plus 4. Or if you do one step further, and then that's a t and divide by 6 and then plus a 6. Okay, so the Python should be t n divided by k multiplied by 2, and then plus a k plus k multiply 2. Okay, so this will be the Python, and then where do we stop? We are gonna stop either when we get down to 0 or we get down to 1. But anyhow, well, we are stopped at, say, well, let's say n minus k multiplied by 2 equals 1 or 0. So those are 2 stop conditions, but it doesn't really matter too much. And in this case, and k will be n minus 1, and then divided by 2, and then you can say this is a floor division, and then it should be accurate enough. Or if you simply say it is a n divided by 2, I'm gonna take it. Okay, so this is the stop condition, and after that, and you can do the further analysis using the iteration, and then this is my idea of how to analyze this code. And for this code analysis, I think the tricky part is, well, how do you find the Tn of this recursive step? We can work on a small example, and then you will find that for each iteration, we are reducing the problem size by 2. Okay, so this is the observation and lead us to this recursive version of the Tn. Okay, so this is the end of this video, and I hope this video can help you get better idea about the questions you're going to see in the midterm. Okay, bye.